And pyroclastic materials. So lava first. We're going to, this is a summary slide. So we'll look at lava, then we'll look at pyroclastic material. And lava, there are many different structures that shield volcano lava can make. We're going to look at three, but you can look at many others in your discussion of and search of materials that come out of shield volcanoes. So first, lava tube. So I'll come back up to this. Lava tube we introduced last time when we talked about how lava comes down the side of a volcano and the top of the lava cools and it insulates the material that's inside, and the inside material that's still liquid will drain away, and you end up with these hollow tubes. Hawaii is filled with these. A lot of people go caving in these huge lava tubes. They can be as small as the size of your finger or as big as this room, and they can go for miles. So this is a picture of a lava tube. Again, the material's draining away, and you're left with a hollow tube. The next neat kind of structure that shield volcano material makes is something called pillow lava. And what happens is this forms underwater. So the water is very cool. We'll learn about properties of water. It's very, very able to pull heat away from other things. So you have an eruption underwater, and the outside of that gets cooled very quickly, more quickly than on land. But lava's still coming out, so it bursts away, and then you have another blob that cools very quickly, and it bursts away, and you get these successive bursts of lava that then quickly cool, and the net effect is it looks like there's pillows scattered along the seafloor. So pillow lava is stuff that is only formed on the seafloor. However, through tectonic changes, and you can watch this video if you're interested when you're looking at the slides on Canvas, you can see lava, pillow lava being created. Through tectonic processes, it can be exposed above the surface later. This is in Oman, and you can see it was the seafloor, it's tipped upwards, and there's the pillow lava in a vertical sense. Another type of lava structure is called Pahoehoe. This is the Hawaiian word for rope. And so what's happening here, the lava's almost cool, and it is bunching up on itself. For scale, there is a Swiss Army knife. And the net effect is it looks like coiled rope. So that's Pahoehoe. So there are many other structures, this blocky, irregular shaped lava, but these are three structures that lava can make in a shield volcano. The next type of material that comes out of the volcanoes that are stratovolcano in nature are pyroclastic material, and I will show you pictures of all of these. But really what we're dividing this material into is particle size. So the first stuff which we've seen pictures of, and I'm going to show you some video footage of Mount St. Helens, probably right after this, is the finest material, pyroclastic, remember, broken up fire rocks. Pyroclastic debris, ash is the finest particle size. It's less than 2 millimeters in diameter. So if you have 2 millimeters in diameter each particle or less, then it's classified as ash. Recall that this can be borne long distances on the wind. We talked about Mount Pinatubo in the Philippines. The ash encircled the entire globe and started coming back around again. And it cooled global surface temperature by about 1 degree to 2 degrees Celsius. So that is ash. We'll look at ash that comes out of Mount St. Helens and its sideways eruption. That ash actually covered 11 states in the United States. So it can go for long distances. The next is lapilli, little chunks of pumice, larger particle size, cooled lava, greater than 2 millimeters in diameter, 2 millimeters up to about 64 millimeters in diameter. So, right, little chunks of pumice, little pieces of rubble. The next are bombs. These are really cool things. What happens in a bomb is you have a lot of gas that we'll talk about that's coming out of the volcano, and it ejects forcefully a blob of magma. And now it becomes lava, it's outside of the volcano. If it cools, if it's rather splats before it cools, you just have a splat of lava. If it, though, gets ejected with enough force for it to cool in the air, it will attain a fusiform shape, so football shape, and it will cool, and then when it hits the ground, you have essentially a stone football. And these are called bombs. Tephra, show you a picture of this. It's just a combination of all three of these things. You'd expect to find this fairly close to the volcano. I'll show you some geologists standing on tephra. So that is the pyroclastic material, here's some pictures. This is ash and lapilli, ash close up, and then you can see again it comes out huge, huge, huge plumes, can be miles high. There are little chunks of lapilli that are in someone's hand. Here's some pictures of bombs. And for scale, there's a geologist rock hammer, which is about this big. So you see some are more spindle-shaped and some are more spherical, but mostly you have this football shape, and they get shot through a volcano, cool in midair, and then land. By the way, this is lying, these bombs are lying on a field of lapilli, so you see bombs and lapilli here. And then tephra is a combination of all three of the materials. This is the side of Crater Lake, and you can see large to small particle sizes for scale. There's some geologists there. So to take a little diversion, in teaching this elsewhere, I was begged by students to let them see the Mount St. Helens eruption. So I'll show you ash, lapilli, and bombs all coming out. I'm going to fast forward to the point at which it erupts. There we go. So just about 30 seconds.
The volcano's northern flank collapses in the largest landslide in recorded history. Largest landslide in recorded history.
Remember, this is the sideways.
It releases millions of tons of magma in a colossal explosion. A cloud of searing gas and rock, known as a pyroclastic flow, races over the surrounding countryside. Forests are flattened. Four miles below the summit, an enormous lake is choked with debris. The eruption continues to shoot poisonous steam and ash miles into the air.
It was just, again, astounding is the best word to describe what happened in 1980 here at Mount St. Helens.
The northern slope of the mountain is buried in several feet of ash. Virtually all life is extinguished. 57 people are dead. They include loggers, campers, scientists, and a reporter. Some are up to 13 miles away in areas considered safe. The plume of steam and ash rises miles into the sky for the rest of the day. The drifting ash cloud disrupts air traffic for hundreds of miles. The scale of the destruction is enormous.
So that is a little diversion to show you the power of the ash lapilli and bombs. Leave that. Okay. So we've been dancing around this notion of the fact that some volcanoes are more dangerous than others, and we know that the little tiny cinder cones or tephra cones are called. They're not dangerous at all, but shield volcanoes, the largest volcanoes, are also not very dangerous. The stratovolcanoes are tremendously dangerous, and there are three factors that control whether the volcano is violent or not. And they're fairly simple factors. But what they're doing is controlling and governing the viscosity of the magma and then lava as it comes out. So the viscosity is a measure of the thickness. When we're talking in engineering terms, we're talking about the resistance to shearing. But the more viscous a liquid is, the thicker it is. So think about molasses as an example if you don't have an intuitive feel for viscosity. If you take molasses and put it in the freezer, it's almost frozen, right? Almost solid. put it in the fridge. It's thick. You can put a spoon in it, and the spoon will stand up, right? If you take it out, put it on the table, the spoon, if you put a spoon in it, it will slowly move over. You're lowering the viscosity, the resistance to shearing. If you put it in a pan and turn the heat on, then it will behave pretty much like water. What we want when we are looking at magma is the analogy of this molasses being like water. You want it to be not viscous, because then you have those nice structures that come out, lava tubes and pillow lava, that sort of thing. You don't have the Mount St. Helens type of eruption and the bursting and violence associated with stratovolcanoes. So viscosity is the thickness, the resistance to shearing. I have a slide again on each one of these, so this is a summary slide. We're going to look at the temperature, the chemistry, and the amount of volatiles. And this will govern, more or less, volatiles less so, but the violence of eruption. Volatiles don't influence the viscosity, but they influence the violence. Whoever's talking, can you please stop? It's really distracting. So temperature. First of all, we want the temperature to be high. We want a very hot temperature magma. This is high temperature magma, and you can see it's just sort of flowing. So when we're talking about high temperature, we're talking about something like 1200 degrees Celsius would be a high temperature magma. When you have it very hot, bonds are not able to be formed, right? Thinking about Bowen's reaction series yesterday, minerals starting to crystallize out. So bonds are not formed, and so it behaves like a liquid. When you have a lower temperature, and by lower temperature, I'm talking about something 700 degrees, 750, 800 degrees, that's a low temperature. Lots and lots and lots of bonds have formed, and so the material is very viscous, very thick. So that's one of the reasons that a shield volcano is not violent. The material comes from deep within the earth, right? Especially if you're talking about a hot spot, it's very hot. When you're talking about a stratovolcano, remember these are ones that are found on land, and so you have subduction, right? Creating a subduction zone. The subducting plate will melt, and it will send fingers of magma up through the continental crust and lithosphere, 35 to 70 kilometers it has to travel through, and it's getting less and less liquidy. It's becoming thicker and thicker. So by the time it rises up through that whole lithosphere and is erupting, it's under tremendous pressure, but it's also almost solid. So you have this very, very violent eruption. So that's the temperature. And then chemistry. And by chemistry, we're really talking about, talking about silica. Silica content of igneous rocks is high regardless. So when we talk about a low silica content, we are talking about basalt, which I said before is about 50% silica. So that's considered low. High is 70, 75%, and we're talking about rhyolite. And the thing about silica is that it bonds with itself. It bonds readily with anything else. So it's really the first thing that starts making bonds, and bonds are what makes it more viscous. So the more silica, the more likely bonding is going to happen at higher temperatures as well as lower temperatures, and the thicker the magma will be. So basalt, again, if you want to watch the little video of pillow lava forming, you see it just runs out. And rhyolite has this violent burst of very, very thick magma that's under high pressure. So that's the chemistry. Really, we're looking at silica. And the last thing is volatile content, which is dissolved gases. And this is a picture, a diagram. We don't have to focus too much on this diagram, but the amount of dissolved gases does not factor into the viscosity, but it is absolutely directly related to the danger level, the hazard level, how dangerous it is, how violent it is. When the dissolved gases that are in magma are high, then you have a very violent volcano. When the gas content is low, then you have a not very violent volcano. And what kind of gases are we talking about? Water is the main gas, but there are also a number of other gases that we'll look at in a minute that cause the magma to become very violent. So this is what I want you to look at, this part here. when the magma chambers deep underground, and we introduced this concept last time as well, it is under tremendous pressure, right? Gravity's pulling on everything above it, so it's under tremendous pressure. Liquid, whether it's water or magma, is virtually incompressible. It's not easily compressed or expanded, but gases are tremendously expandable and compressible. So what happens is down here, the volatiles are in a very, very small, microscopic even, pore space. And then as the material starts to rise up in the volcanic neck, the gases start to become under less pressure, and so they'll expand. And the process of expansion causes more pressure, so it's this self-perpetuating cycle. The magma will rise up faster because it's under higher pressure, which will cause the bubbles to expand even more, which will put more pressure on it and will cause it to rise up. By the time you get to the top, you have these huge amounts of gases, dissolved gases. Again, water turns to steam because this is very hot. And you have violent bursting eruptions. This is similar to, if any of you are scuba divers, why you can't be at the bottom of the seafloor and then rise up quickly to the surface, right? You get the bend, right? You have a big problem. When you are underwater, very, very deep underwater, you're breathing oxygen on demand through a regulator, right? And so the regulator will give you as much air as you want from this compressed air tank. And at the surface, your lungs can hold about 2 liters of air, right? But you can imagine if you take those 2 liters of air and put them at the bottom of the seafloor, it is compressed into a very, very tiny space. Your body doesn't crush because you're essentially a bag of water, and so the crushing weight of the pressure around you is not a factor. The only factor is your lungs and any pore spaces, any head space where there's air. So you breathe in the equivalent of, I don't know the number, but maybe 20 liters of air if it were at the surface, but it fills your lungs comfortably. And then that will come into equilibrium with your blood, right? So the bubbles of oxygen, microscopic bubbles of oxygen that are going through your bloodstream are small. But if you rapidly come up without having your body essentially process the fact that you have a huge amount of pressure in gases in your body, then you can have an embolism. You have these gases expand. So you have to come up very slowly, and if something happens and it's a question of having an embolism or dying, you do a free ascent. You can't get any more oxygen. It's kind of cool. They have you practice this when you're scuba diving at a safe depth. You can breathe out. It's really interesting to do. You breathe out, and you go up as slowly as you can, but you keep a steady stream of exhalation for minutes, because as you're coming up, it's expanding and expanding and expanding, and you just keep breathing out. The worst thing you can do is hold your breath when you're going up. Guaranteed your lungs will explode. So it's the same thing that happens in scuba diving that happens in these volcanoes. So you have tremendous, tremendous pressure at the top, and you have violent bursting. So those are the 3 things that control the violence of eruptions. And one note about this is you have to take all 3 of them together and figure out what's going on together, because, for example, basalt has a huge amount of volatiles in it usually, but it's not very viscous. There's not a lot of silica, and it's usually a very high temperature material that's coming to the surface. So the bubbles that are there don't make for a violent situation. They bubble out like soda, right? If you're looking at soda bubbles, they just go out. So you have to take these 3 things together to figure out how dangerous a volcano is. So those are the viscosity and sort of explosivity levels. Let's now look at some of the hazards associated with volcanoes. So again, summary slide. I have a slide on each one of these. Lava flows we will look at, so I won't say anything because we're going through these. Tephra, New Erdont, I'll show you a picture of one fun. Lahars, and then poison gases, really fun thing to look at. So first of all, the lava flows. What did we say about lava flows? How dangerous are they in a shield volcano? Excellent. So that's a stratovolcano, absolutely. By the time the lava comes, you're already dead from the other things. Right, excellent. What about in a shield volcano? Excellent, thank you. Yeah, not at all, right? We can go film it. However, we looked at the trees that were being essentially carbonized, turned into charcoal by the lava that's coming through. So when you're talking about lava flows, they're non-issue in a stratovolcano because everything's gone by the time it comes out. When you're talking about a shield volcano, this can be a hazard to stationary items. If you can move, you're fine. Trees, roads, bridges, homes, anything that's stationary can be caught on fire by lava because it's coming out and it's so hot. Remember, especially shield volcanoes, 1400 degrees Celsius. It touches something, it can burn it up. So lava flows can be dangerous to stationary items. We have to then rebuild or do something about it. There was a bay in Iceland that was a vibrant fishing town or a fishing area. There were towns all around the bay where fishermen lived. And a lava eruption was going along the mouth of the bay and threatening essentially to close the bay. And this became a serious concern for the people in these towns because, right, their livelihood is predicated on fishing in this bay. It was a great place to fish. So they knew that if the bay closed, the water would dry up, water wouldn't replenish, and all the fish would die. So they did all sorts of things. They were planting dynamite to try to get the lava that is almost cool but not quite to explode and become sort of a rain of lapilli, if you will. They had the fireboats go out and suck cold water from the bottom of the ocean and spray it on there to try to chill it. And they successfully kept the bay open. Or did they? It's really hard to kind of figure this out because maybe the eruption was just over anyway and it wouldn't have closed. But they sort of said, yeah, we did it. We stopped the lava flow. So that's a danger, again, not to you, but to other things. Tephra is what you saw when you just watched the Mount St. Helens little clip of it going off. Tephra is a combination of ash, lapilli, and bombs, recall. And if you're standing too close to a stratovolcano eruption, this is the stuff of stratovolcanoes, not shield volcanoes, you get a rain of sometimes molten, sometimes very, very hot material falling down on you. So this is a hazard because it can burn you, it can burn other things, it can set things on fire, and it can cover over things. But it's not pleasant to be in a rain of tephra. That is not a good situation. And you read about some people who have been in a tephra flow in your book. So this is Arenal. I showed you Arenal during the daytime, and now here we have Arenal at night, and you can see a new Ardent coming down off the side of the mountain. So again, there's a small ash eruption. This isn't the main eruption. Ash is coming out, and it comes out so hot that it's molten, it's glowing, and when you have a big eruption of ash, it will roar down the side of the mountain, so you see this glowing ash cloud. You can imagine, just like with tephra, this wouldn't be a good situation because you have molten ash. Ash, as you'll see in the supervolcano film, if you haven't already watched it, is hazardous to many things. It's hazardous to you because your lungs are, it's like inhaling microscopic razor blades. So it will cause your lungs to fill with fluid and you can asphyxiate breathing this ash. It's also hot, can burn your skin. So the prisoner of St. Pierre that we talked about in Martinique, in Mount Pelée, was horribly burned by this heat and by the ash. So New Ardent glowing ash cloud incinerates things, burns you, burns other things. You saw a little bit of Lahars in the St. Helens picture, and you'll see a number of Lahars in the video Supervolcano. So this is a picture of a Lahar after Mount St. Helens, and so recall that the New Ardent, essentially the ash, the glowing ash cloud and the cooled ash, is still quite high temperature. It will melt any snow, if there are snow-capped peaks of the volcano, or it will mix in with water because any sort of mountain is considered a headland for a watershed area. So water will be mixed with the ash, and it becomes the temperature and density of hot cement. It is very, very high temperature, and it will roar down, occupying the lowest area on the landscape, which is a river valley, and it will come through and just cut off trees, as you can see at the stump. If you were to go grab these trees, they might be more like charcoal than they are wood because they've been moved through this hot material. And again, lahars are very persistent. We talked about Mount Pinatubo in the Philippines and how the United States had to close the Air Force Base because for 10 years after that eruption, in 1990 it erupted, for 10 years after that, every time there was a storm, we'll talk about hurricanes later, every time there was a storm, the lahars would get re-wet and would saturate and come back down and coat the landing strips and coat everything. So they can be quite persistent and quite devastating. So those are lahars. And then poison gases. Again, water vapor is a main gas from these volcanoes. So carbon dioxide is another gas, and we'll talk about the hazard level of each one of these. Carbon dioxide is not terribly lethal to you, right? But if you're in a cloud of all carbon dioxide, you wouldn't be able to breathe. It would be very uncomfortable. You could asphyxiate. So carbon dioxide comes out of volcanic eruptions processes. Sulfur dioxide is this sulfurous rotten egg smell. It can give you a stomach ache. It is not pleasant, but nor is it lethal. So that's another gas. So the water vapor, then carbon dioxide, sulfur dioxide, SO2. Carbon monoxide is a common gas in these eruptions, and we're talking now about both types of volcanoes. We're talking about shield volcanoes and stratovolcanoes. Carbon monoxide, as you may know, is very similar to the oxygen we breathe. O2 and CO are similar in terms of their weight and their behaviors. So our body can't tell the difference between carbon monoxide and oxygen. And so when you're breathing it, you don't even really know that you're breathing anything bad. If you're breathing all carbon dioxide, it would be very uncomfortable. You would get the feeling that you're asphyxiating and can't breathe. Carbon monoxide, your body just uses it as it uses oxygen, but then you feel very sleepy and you do go to sleep, but you never wake up. So carbon monoxide, not good in terms of gases. Sulfuric acid, H2SO4, there are a number of acids that will be volatilized, that will be in a vapor phase. So sulfuric acid, again, H2SO4, if you're looking at the chemical formula, is an acid. So just like ash not being good for your lungs, if you breathe in acid, your lungs are your most sensitive organ to many different things. It will singe away your lungs. You won't be able to breathe. And if you're getting it on your skin, it will eat away your skin. So sulfuric acid, not good. Hydrochloric acid, which is HCl, is also not a great gas to be breathing or to have on you because, again, it can singe your lungs. Your lungs will fill with fluid. You'll asphyxiate. But then also it can burn off your skin. So that's hydrochloric acid. And the last gas that comes out, this is not an all-encompassing list, but sort of the gases that are common, is something called hydrofluoric acid. And hydrofluoric acid is a very, very, very dangerous acid. We geologists use it actually to date the age of rocks because it can dissolve rocks. It dissolves away anything about rocks except for zircons, which we then can take them and use them to radiometrically date how old the rock is. What would happen if you were to be in the presence of hydrofluoric acid is if it got on your skin, you would not have a burn or a rash like you would with hydrochloric or sulfuric acid. It's a target acid. And so what happens is it goes down into your bones. May or may not leave any red spot on you. It goes into your bones and it eats away your bones. And I saw this sort of scarily when I was doing my PhD at Syracuse. I came in on a Saturday, had my dog and my coffee walking down the street, and I down the hallway, and I heard this woman screaming from the clean lab. It's like, why is there a woman screaming in the clean lab? I was the only woman in the department. So I would make the person who gets killed first, right, in a horror movie, because instead of going to call someone, I went looking for the woman to see if I could help her. And it wasn't her, it was my friend Greg, who radiometrically dates rocks, and he was carrying a beaker of hydrofluoric acid. And this freak accident, the fire door spring broke and smacked into it, and he splashed some hydrofluoric acid on his toe. And so he was, when I went in there, he was in his underwear in the sink screaming and was blasting water at his foot. He was okay eventually. He had to take these massive supplements of calcium. His foot is a little floppy. His bones are impacted by this, but yeah, it was a bad situation. So I think 2 teaspoons, if memory serves, is enough to dissolve all the bones in your body. So this is not a good situation to be in the presence of hydrofluoric acid. You become floppy. So poison gases are not good in a volcano. And these are endemic to both shield volcanoes and stratovolcanoes. So I want to remind you that on Monday, the 15th, we are going to watch the thrilling conclusion of the supervolcano film. This film is something that I was going to show in class, but because of the snow and the situation with not being able to get here, I gave you the link to it. So supervolcano, the conclusion will be shown on Monday the 15th. If you prefer to watch it at home, then you're very welcome to watch it at home. You don't have to come to class, but that will be the last 50 minutes. The movie is actually 2 hours and 20 minutes long. So since it is mandatory, I wanted to end class early to give you that class time, 2 hours and 20 minutes to watch the film. The film is mandatory. The film will be on the quiz. And if you have any questions, so you had a question, yeah?
What's the part of the rock that doesn't break down?
Oh, zircons. Z-I-R-C-O-N-S. Zircons are the thing, yeah, the thing that hydrofluoric acid doesn't break down. So any other questions? Okay, so we'll end now to give you enough time to watch the film. We'll pick up on Friday, and we are going to start with earthquakes.
Just a quick question about the quiz. I'm sorry you've already answered this. So with the we just add 12 points onto the grade that is on campus.
Right.
So that's not already
put a
baked.
column. I put a separate column, so the running total is what your first quiz grade is. So you add 12 points to the grade on campus.
Add 12 points to the grade that's on campus.
Right, but I put a column that says quiz 1 scale,
Right.
so you add it.
Fantastic. Thank you so much. Sorry.
No, it's no problem. I'm sorry. I meant to talk about it in detail in class, but
Right.
with the snow, it just didn't, you know.
Thank you.
You're welcome. Okay.
So higher temperature
It's better.
better and less violent.
Right. Because there's no bonding going on, so it will behave more like a liquid. It will just flow out like water. If it's lower temperature, then there's a lot of bonds. It's really thick and viscous, so when it bursts away, it's violent. Yeah.
I was just wondering if I'm thriving, would it be possible to come and like go over my test? I just wanted to see what I got.
Of course, yeah. Yeah. Oh, I'm gonna shut this off.
So higher temperature is better because like it'll make the plasma more liquid, which is safer.
Right.
So low temperature would erupt solid.
Yeah, really thick, and so it will explode and burst.
And low temperature happens in shield volcanoes. Is it shield volcanoes?
Oh, no, stratovolcanoes is low temperature. The stratovolcanoes low temperature, shield volcanoes high temperature.
I was just wondering what is this? Can we just add that to our supervolcano?
Yeah, so there's a column on campus now, so the running total is actually your first quiz
Oh,
grade.
okay.
So you add those two together.
Okay, out of 100, and then that's our quiz.
That's your quiz grade. Yep. Yeah, you're welcome. Good. I hope that it works out.
That was one of the last scenes, Rose.
Good crowd. Yeah, excellent. If you want to send the link, I put it on Canvas, or you can put it on